Hello and welcome to this Bioprocess International Ask the Expert webcast. I'm your host, Leah Rosen, online editor for Bioprocess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions. Your questions in the question and answer window are only visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Zhumei He from Bio-Rad Laboratories.
Thank you, Leah, for the introduction. Today, I'm going to talk about the use of buffer additives in mixed-mode chromatography for the optimal target purity and recovery. Chromatography is a separation technology based on the interactions between molecules in a solid surface. For column chromatography, molecules with a stronger affinity for the resin will move slower along a column, and they're separated from those interact weakly but move faster. The common types of interactions are shown in the table. For the mixed-mode chromatography, we are going to discuss two or more forms of these interactions are typically involved. There has been a long history of research and discovery of mixed-mode chromatography materials. Here I list the major milestones. In 1956, Theselius and his co-workers prepared a column using the calcium-containing mineral hydroxyapatite, which they found spectacular for protein separation. As time passed, we got to know more about the interactions between hydroxyapatite and the biomolecules. In the old days, Theselius used the fine crystals of hydroxyapatite to pack his columns. Those columns were fragile, they could not be run fast, and probably didn't last many cycles either. In 1986, the Kodayak team developed a procedure to prepare the ceramic form of hydroxyapatite. This new spherical material is mechanically strong and chemically more stable. It has been widely used in bioprocessing ever since. Over time, we have seen increasing numbers of mixed-mode chromatography media on the market and their emerging applications in bioseparation. The newer resins are polymer-based, with their surface modified with various charge and hydrophobic functionalities. This is a diagram that we often see in textbooks teaching ion exchange chromatography. To come up with a purification strategy, we have to estimate the isoelectric point of the target protein first, either experimentally or by calculation from its encoding DNA sequence. When the purification is performed at a buffer pH higher than the pI, the target protein will be negatively charged, and it will be bound by an anion exchanger. We can also choose a cation exchanger if we prefer to run separation at a pH more acidic than the pI. For ion exchange chromatography, proteins are typically loaded onto a column at low conductivity and then eluted by a high conductivity buffer. For a mixed-mode chromatography resin with both charge and hydrophobic functionalities, the effect of buffer is a little more complicated. When the buffer conductivity increases, the electrostatic interaction between proteins and the resin will be weakened. At the same time, the hydrophobic interaction could be enhanced. A protein may use alternative modes to interact with the resin in response to buffer conductivity change. As the protein's charge state is pH dependent, its binding and elution selectivity can be achieved by buffer pH and conductivity variation. In today's presentation, I would like to focus on the use of buffer additives to manipulate these interactions in order to achieve the desired chromatography separation. This is a list of common buffer additives used in protein chromatography. Guanidine hydrochloride interacts with the amino acid side chains, and urea has been found associated with peptide bonds. Their effects are so strong that they might unfold proteins. These chemicals are often used for stripping the strongly bound proteins during column regeneration. Arginine has gentle impacts on electrostatic and hydrophobic interactions, as well as hydrogen bonding. It's often used for minimizing non-specific interactions. Propylene glycol makes electrostatic interactions stronger. Glycine is the opposite. It enhances hydrophobic interactions. Now, let's take a look at a hydrophobic cation exchanger, Nuvia cPrime. This resin has an excellent tolerance of feed stream conductivity, as there is a hydrophobic phenyl group in the ligand structure. The Nuvia cPrime ligand also has a carboxyl group with its pKa at around 5. When the buffer pH is below 5, the Nuvia cPrime ligands are in their protonated form and appear uncharged. The resin would behave like a typical HIC media. At pH higher than 5, the carboxyl groups will be ionized and electrostatic interactions become dominant. We can use the resin just like a cation exchanger. In either way, this resin offers good clearance of whole cell nucleic acids. There is also an amide bond in the ligand structure. It can serve as hydrogen bond donor or acceptor, providing additional mechanism to engage biomolecules. A MAD team has studied the effect of arginine for a MAD polish purification with Nuvia cPrime. The feed stream contains 96% of MAD monomer. The goal is to improve the monomer content at high recovery. The initial observation was high elution pH or high arginine concentration in buffer would provide excellent MAD recovery, but the product purity was compromised. The effects of buffer pH and arginine were correlated. This scientist decided to choose 3 conditions for further evaluation. For condition 1, the MAD elution was performed at high buffer pH without any arginine. For conditions 2 and 3, a lower buffer pH with different arginine concentrations were used. For condition 2, the bound MAD molecules were eluted with a buffer containing low concentration of arginine at a lower pH. The monomer content of the LUH was excellent. However, the product recovery was 70% only. Similar product purity was obtained from conditions 1 and 3. Condition 3 provided the best monomer recovery when a buffer with high arginine concentration and low pH was used. Based on these results, the scientists selected an elution condition that balances the need of aggregate removal, monomer recovery, and process economies. Nuvia aPrime4A is a hydrophobic anion exchanger. In its ligand, there is a quaternary amine and a phenyl group. At near neutral pH, the high pi proteins would carry positive charges. When loaded onto the column, they will likely appear in the flow-through fractions due to the electrostatic repulsion from the ligands. On the other hand, the low pi proteins should be bound strongly through electrostatic interactions. Therefore, a bind and elute strategy will be appropriate for the purification of acidic proteins. Buffer pH and conductivity impact both charge and hydrophobic interactions. This allows us to fine-tune the selectivity and recovery for target protein molecules. As I mentioned earlier, glycine enhances hydrophobic interactions. We are all familiar with the use of high conductivity buffers to promote protein binding onto a hydrophobic resin with salts like ammonium sulfate or sodium chloride. However, glycine is a sweeter ion. It does not affect buffer conductivity much, and we will use only modest concentration of glycine in mixed mode chromatography. Glycine is also known stabilizing proteins during purification. Here, we have a pair of acidic proteins, human serum albumin and soybean trypsin inhibitor. Their PIs are essentially the same. Although the crystal structure of HSA does show a few hydrophobic patches, these two proteins are not separated by traditional anion exchangers. They were bound by Nuvia aPrime4A when the column was equilibrated with a buffer containing 100 millimolar glycine at pH 7.5. When we apply a gradient between buffer A and buffer B to the column, only HSA was eluded. Buffer B doesn't have any sodium chloride or glycine, and its pH is 4.5. During the course of the gradient, the negative charges on HSA were neutralized by the acidic buffer. This minimized the electrostatic interactions between the protein molecules and the resin. At the end of the gradient, glycine was eliminated from the system too. There's no more hydrophobic interaction. The bound soybean trypsin inhibitor would stay on the column until we apply a second buffer that contains 1 molar of sodium chloride. This result indicates that the STI was bound through strong electrostatic interaction. With the use of glycine, we were able to resolve these two proteins on Nuvia aPrime4A column. In the next case, I would like to talk about the purification of a recombinant protein overproduced in E. coli. The target accounts for 2 to 5% of total proteins in the crude extract. This acidic protein is not stable when the buffer pH is below 6. Several anion exchangers and HIC resins were evaluated, and their purification performance was not satisfactory. Either they did not bind the target efficiently, or the final purity or yield were too low. Nuvia aPrime4A was selected for its efficient target capture capability, without the need of extensive phase stream manipulation. However, the elution of the target protein remained challenging. Sodium chloride was not effective, and high concentration of arginine, up to 750 millimolar, was needed for its elution. We thought it was too expensive, so we decided to search for other buffer additives to facilitate the target elution. The effect of salts on hydrophobic interaction has been well studied. Particularly, some divalent ions, such as calcium and magnesium, have been shown enhancing protein solubility in aqueous solution. They have also been used for the elution of proteins from HIC resins, so we decided to give it a try. We perform a DOE investigation on target elution. The parameters we are looking at include the elution buffer pH, sodium chloride concentration, and additive magnesium chloride concentration. The contour plots demonstrate the possible interactions between these parameters, and they are not independent. For target purity, the optimal pH is 8.5. At this pH, high purity of target can be achieved at 2 spots for sodium chloride, from 100 to 200 millimolar or 350 to 400 millimolar. The magnesium chloride concentration should be no more than 200 millimolar at pH 8.5 in order to have a target purity at 80%. For target recovery, the optimal pH, again, is 8.5. At this pH, 400 millimolar of sodium chloride would provide the best target recovery. The optimal magnesium chloride concentration is 200 to 300 millimolar. This is slightly higher than the concentration needed for the best target purity. For this capture step, we decided to give up the purity a little and shoot for the best recovery, as we will have a polished purification step later. To scale up the purification, we loaded the culture harvest directly onto a column, followed by a wash with a buffer containing 200 millimolar sodium chloride at pH 7. The bound target was eluted with a tris buffer containing 400 millimolar sodium chloride and 250 millimolar magnesium chloride at pH 8.5. As shown in this electrophoresis image, the target purity was 80% and the recovery was 90% from this capture step. This is a huge improvement from the initial conditions. Finally, I want to spend a few minutes on CHT, the mixed-mode media with the longest history in bioprocessing. There are two types of interactions possible during CHT chromatography. The electrostatic interactions between the phosphoryl groups, also known as the P sites, and the basic residues on the proteins, such as arginine and lysines. Chelation complex can form between the calcium ions on the hydroxyapatite, also known as the C sites, and the acidic residues of the protein polypeptides, such as aspartate and glutamate. Interaction at the C sites is believed to be much stronger than the electrostatic interaction at the P sites, at least 60 times. Elution of the bound proteins can be achieved by increasing concentration of sodium chloride or phosphate or both in the buffer in combination with pH variation, depending on the strength and types of the interactions. Just like the earlier cases, we use DOE for chromatography condition screening. Besides the buffer pH, sodium chloride concentration, and sodium phosphate concentration, we also look into the effect of calcium ion on the binding of the target and acidic enzyme this time. The pI of the target enzyme is around 6. Some of its acidic residues might be available for chelation at the C sites. DOE results shown that the addition of calcium ion in binding buffer improved the binding capacity for target enzyme. We speculate that the calcium ions serve as bridges between the carboxylates of the protein and the phosphoryl groups on CHT. Interestingly, in this case, sodium chloride also helps target binding. The sodium ions might interact with either the phosphoryl groups on CHT or the carboxylates of the enzyme and suppress the repulsion between these negative groups. According to the DOE prediction, we scale up the purification. The target enzyme was bound by CHT in the presence of 200 millimolar sodium chloride and 1 millimolar calcium chloride at pH 6.5. And it was eluted with 75 millimolar sodium phosphate. Highly purified enzyme was obtained. With an acidic pI, this enzyme should carry negative charges at neutral pH. We anticipate a strong repulsion between the phosphoryl groups on CHT and the carboxylates of the protein in the absence of calcium ion and sodium chloride in the binding buffer. This was confirmed by the DOE screening and modeling. So we also tried to purify the enzyme in a flow-through mode. The column was equilibrated with a buffer containing 5 millimolar sodium phosphate and only 5 millimolar sodium chloride at pH 7. Impurities were effectively retained by the CHT column, while the target enzyme was in the flow-through fractions. In this case, the calcium ions played a key role in the purification mode switch. Here is the summary of my presentation. Multiple interactions may take place between the mixed-mode resins and biomolecules during chromatography separation. By the variation of buffer pH and conductivity and the use of additive, we can resolve similar protein species, eliminate impurities, and recover the target molecules in good yield. The chromatography operation can be run in a flow-through mode or bind-loop mode, depending on the purification need and the process economy consideration. Method development for mixed-mode chromatography is not necessarily different or more difficult than other types of chromatography. It's intuitive on the basis of our knowledge about the interaction mechanisms. DOE is often used for initial condition screening, just like we have been doing for all other chromatography. Before I conclude my talk, I would like to let you know that we have a global support network to assist you with method development, process transfer, and regulatory procedures. Our technical support group can help you on the phone or by email in case you have any questions or issues throughout the lifetime of your product. To facilitate your screening, we offer resins in 1 or 5 ml pre-packed columns, 96 well plate, 200 or 600 microliter robo columns, as well as 25 ml resin slurry in bottles. You can request samples and literature online, or you can also speak directly to our scientists and request a custom seminar delivered to you virtually or on-site. Thank you for joining me today, and I'm ready to take any questions you might have about my presentation.
Okay, great. Thanks, Shumi. So the first question is, where can I learn more about how to start design of experiment studies with additives?
Oh, great question. All this data has been published. We have the app notes on the website, and you can just go to the website biorad.com library to search for this app notes. Of course, if you can leave your contact information, we can email you. In a particular topic you're interested in, we can email you the tech notes on that topic. And also, if you prefer, you can reach out to our process specialists and tell us the particular purification needs you need help. We are more than happy to organize a custom presentation either on site or virtual webinars, which will focus on your particular purification challenge and the proper DOE strategies.
Okay, and can DOE results be analyzed without the need for an analysis software program?
To be honest, in order to do a more quantitation of the parameters effect on the purification, you will need the software in order to do that. And if you currently do not have access to the software, you can reach out to us and we'll see how we can assist you. And another point I want to make is if you completed your DOE study and would like to discuss with us about the data interpretation or further method development optimization, scale-up strategy, please do not hesitate to contact us.
Okay. And can it be a regulatory problem to have an additive in the buffer? I assume the additive needs to be removed after or tests need to be performed that show that the additive does not end up in the final API formulation.
This is a great question. It actually depends on what you are adding. On the other hand, the ones I'm showing today, those are very common ones that we've seen in approved commercial production process. But if you have a question about a particular additive that you have not seen in this presentation, feel free to contact us, and we are going to investigate it together with you.
Okay. I want to use calcium to promote target protein binding with high hydroxyapatite. What concentration should I begin with?
Well, actually, you don't really need to have a very high concentration. And as I shown in the presentation, usually I would suggest you begin with 1 millimolar or 20 ppm. And you can also use it in combination with different concentration of sodium chloride that depends on the exact interaction modes. Sometimes they work together pretty well.
Okay, and as a reminder, you can type your questions in. If we don't get to your questions, we will be passing them on to Jume, and she can follow up with you directly. So the last question, because we're running out of time, is what does salt tolerance mean?
In general, salt tolerance, we mean in process purification. It's like you don't have to manipulate the feed stream or the sample a lot in order to achieve a good binding capacity. For example, like as we know that for ion exchanger, a lot of times you are advised to do dilution or reduce conductivity in order to have a good binding capacity. But for most of the mixed mode, like with hydrophobic character resins, you can actually have your buffer with modest concentration of salt and you still have good binding capacity and selectivity. This often can simplify the step transition between your different purification methods without a lot of sample manipulation.
Okay, thanks, Shumi.
Thank you.
And thank you to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at future Bioprocess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.